afternoon, students. My name is Mr. Innocent. Most of you here, I'm the chemistry teacher in the annex. I will introduce the topic we have, as you can see on the board, electrode potentials. This is a continuation of the topic which we ended before you started your mock examination. Remember, we stopped at electrolysis. So electrode potentials is a continuation of electrolysis. In this class, we are going to look at the meaning of electrode potentials. We are going to look at the hydrogen reference electrode. We are going to look at the electrochemical series. We are going to look at electrochemical cells and then talk about electromotive force, which is the EMF. If time permits us, we can move and talk about the application of electrochemical cells. Now, the first thing we need to look at now, we need to look at the meaning of electrode potentials. But let me take this simple example now. For example, if you immerse a zinc rod into a solution of a salt, you immerse a zinc rod into a solution of a salt, you will realize that the zinc rod, from the equation you see on the board, it will lose electrons because some of the ions will dissolve into the electrolyte, which is the ion of what? Of the zinc rod. And the electrolyte we are using for this purpose is zinc tetrahydrosulfate 6. That's the electrolyte we'll be using for this purpose. You realize that once you immerse it in the electrolyte, you'll find that the zinc rod loses electron. Another scenario. If we take a copper rod and immerse it in a solution of a salt, that is copper 2 tetrahydrosulfate 6. As you can see from this equation, we realize that the copper will rather gain electrons. It will rather gain what? Electron. It will be deposited on the rod. This is happening as a result of what we discussed earlier on in electrolysis. Remember, we talked about the electrochemical series. Their position in the electrochemical series determines which dissolve into the solution and which is what? Which is decomposed on the rod. Now, when this happens, when you immerse a particular metallic rod into its salt, a potential difference exists between the salt of that metal and the metal itself. That potential difference that exists between the salt, the metal, and the salt of that metal is what we call electrode potentials. Remember, I just said that the difference that exists between a rod, the metallic rod, and its salt that is in solution, that difference that exists between them is what we call what? Electrode potentials. Having known this now, we are going to talk about standard electrode potentials. Before we talk about that, there are conditions that lead to having a standard electrode potentials. First of all, it has to exist in an atmospheric pressure of 1 atmosphere. Then the temperature must be 25 degrees centigrade, that is 298 Kelvin. And of course, the solution that we are using must have a concentration of 1.0 mole per dm cube. Well, when all this is what is attained, we are going to have a standard electrode potential. Now, I will make a reference to this diagram you have seen on the board here. As you can see, we have a diagram of 2 different solutions. A solution of zinc tetrahydrosulfate 6 with zinc rod immersed in it, and a solution of copper 2 tetrahydrosulfate 6 with a copper rod immersed in it. And they are both connected by a salt bridge. A salt bridge could be just a filter paper. Just cut a very thin strip of a filter paper, immerse it in either sodium chloride or potassium chloride. and you put it in between. The purpose of the salt bridge is to allow for the movement of ions so that there will be flow of electrons between the two different electrolytes or solutions, as you can see on the board. Now, remember in electrolysis, I told you that when we get to electrochemical cells, if you could remember, or those of you that were paying attention in the class, you could remember, I told you when we get to electrochemical cells, I'm going to explain certain things to you, and that is what I want to explain now. Remember in electrolysis, the anode is the positive electrode, and the cathode is the negative electrode. Remember we say in electrolytic cell that oxidation occurs at the anode and reduction occurs at the cathode. In the case of this now, the negative electrode is the anode. As you can see from the direction of the arrow in the diagrams, electrons are moving from the zinc electrode, which is negatively charged, to the copper electrode, which is a positively charged. And because of that movement, and from the initial explanation that we said, where zinc rod was immersed in zinc tetrasulfate 6, the ions were formed, meaning that it was oxidized. Remember in the lecture I told you that oxidation always occurs at the anode. Despite that it is the negative electrode, oxidation occurred at the zinc electrode, which is now acting as the anode. Meanwhile, in electrolysis, this acts as as a cathode. So you must not confuse these two different terms as we move on in this discussion. Now, you may be asked to draw this, but most often in exam session, we are preparing for examination, nobody expects you to start drawing this in the exam situation. This same cell can be represented, as you can see on the board here. I just underlined. This cell, this is a shorthand representation of this cell that you have seen on the board here. So we can represent this cell, this same cell, as this. Where you have, if you can see from this, we have the double arrows, the double vertical lines. The double vertical lines represents the salt bridge, as you can see here. That is the purpose of the double vertical line in this short diagram. Then the single vertical line between zinc metal and the zinc ion and the copper metal and the copper ion, the single vertical line represents the phase boundary. That is the boundary between the solid and the solution. That's what it represents, as you can see from the diagram. So this is directly represented here. And in this case now, when we look at this now, the zinc electrode becomes the right hand there, the left hand cell, and the copper becomes the right hand cell, as you can see. Now, all of this we are saying, we cannot calculate or show the electric potential of a particular metal ion system except we get a reference. And this is moving us to the next thing we are going to talk about, the hydrogen reference electrode. The hydrogen reference electrode was produced by the IUPAC. By the IUPAC. From the SS1, you should be aware of this. We'll be singing it like a song. The International Union of Pure and Applied Chemistry. They gave an arbitrary rule where the hydrogen reference electrode is assigned a value of 0.00. The hydrogen reference electrode, I say this, is giving a value of 0.00 volt. From this, every other metal ion system electrical potential can be measured. Now, whenever we connect it, we are measuring any particular metal ion system. What we do is that we connect it, the hydrogen reference electrode, which comprises of a solution of hydrochloric acid that is produced. Remember I said the standard electrical potential is what? The solution must be in 1.0 mole per dm cube. The atmospheric pressure is 1 atmosphere, and the temperature is at 25 degrees centigrade or 298 Kelvin at any given time. So hydrogen gas is forced through the tube, as you can see, and the electrode is a platinum electrode, as you can see, with a space open in the tube where the hydrogen gas is forced through. Now, whenever you want to measure the electrical potential of any cell, you just connect that particular metal ion system to the hydrogen reference electrode. Now listen to me. Anytime the hydrogen reference electrode is connected to any cell, and electrons is flowing from the metal ion system to the hydrogen electrode, it is going to have a positive, a negative value. It is going to have a negative value anytime electrons is flowing from the metal ion system to the hydrogen reference electrode, which is the standard. At any time that happens, the charge is going to be what? Negative. And at any time, electrons is flowing from the hydrogen reference electrode to a metal ion system, the charge is going to be positive. You should be aware of this. The charge is going to be positive. And now this will lead us to look at what we call the electrochemical series. We dealt with the electrochemical series in electrolysis, as you could remember. The series comprises of, those of you refer back to that. At the top of that series, we have the potassium ion, we have the calcium ion, we have the sodium, and you have it in your notes. Refer back to that series. When we look at that series from the top to the bottom, which at the end of it, you know, if you could remember, is a gold that we have, gold ion that we have at the bottom of that. I remember in electrolysis, I told us that at any time that those ions that are below in the electrochemical series can be easily discharged in the course of what? Electrolysis. The same way in electrochemical cells. If you know what an electrochemical cell is. Every day we say battery. My phone has no battery. I need a battery for my laptop and every other thing. That is what we are about to talk about now. Electrochemical cells. Remember, these are our cells. When you have the zinc rod system and the copper rod system, they are half cells. Whenever two half cells with different electrode potentials are connected, they form a device. That device that is formed is called an electrochemical cell. You can see in other books, they call it galvanic cell, or you can see it referred to as voltaic cell. But generally, we call it a battery. Now, whenever an electrochemical cell is being formed, that device converts chemical energy into electrical energy, which we use for our batteries, for our radios, and every other thing. And as we move further in this topic, you realize that we have different applications of these electrochemical cells, which we have talked about the different type of electrochemical cells we have, which you already know. So as we move on, we'll talk about those different types of electrochemical cells. Without wasting much time, let's look at the electromotive force, EMF, as you all know it from your physics class. EMF. This is a force that is generated as a result of the algebraic summation of two different half cells that are being connected through what is called a bridge. The algebraic summation of two different half cells that are being connected by a solid bridge. What we get, the value that we get when we do that is what we call EMF, which is electromotive force. And the EMF can be deduced by having the difference between the right-hand cell and the left-hand cell. Having the difference between the right-hand cell and the left-hand cell. So we can use this simple formula, standard electrode potential of a cell is equals to electrode potential of the right-hand cell minus electrode potential of the left-hand cell. By the help of this, we can always calculate the electrode potential of the electromotive force of any cell. Please I'll be expecting this assignment to be submitted within the next few days. Thank you very much for watching.